Welcome. So today we're going to talk about auxiliary variables. Now these are propositions that you could introduce to try and capture a particular subformula inside of your theory. Essentially what we want to do is introduce a variable that says it is true if and only if some other formula is true as well. Right? So if we were to take a fairly simple formula here using propositions P or Q, and then we were to draw the truth table for P or Q, I'm going to do P, Q, P or Q. And then I'm going to use the symbols T and F for true and false. Actually, let me avoid that. I'll use 0 and 1. So 0 is false and 1 is true. So we have 4 different possibilities. False, 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 true. Oh, fix this. True, false, and true, true. Of these 4 possibilities, only the first is false, and in every other one, at least one of them is true, and so we have ones down here. Now an auxiliary variable, if we want to tie it to this formula P or Q, we essentially want to equate the two. And the way we do that in propositional logic is an if and only if. So what we're going to write is our new auxiliary variable x0 is true if and only if our formula P or Q is true, right? And so essentially what we're looking for is a representation that says x0 takes on exactly the same values as the formula P or Q. So 0, 1, 1, 1, right? Now in propositional logic, we just break this down. This is the regular implication that you've seen. It just goes both ways. And so this is really telling us two different things. For this auxiliary variable x0, it's saying that if x0 holds, then I want P or Q to hold. And it's also saying that if P or Q holds, then I want this auxiliary variable to hold. Right? And if we wanted to apply the typical De Morgan's rules and distribution, we could do that now with x0 just to break it down a little bit further. And so in the first here, we might have something that says not x0 or P or Q. Right? Now if you look at this formula, what it's going to say is that if P was false and Q was false, both of these equate to false, it means that this must be true, right? And the only way to make not x0 true is to make x0 false. And so this matches the first line that we have here. So you can see how this sort of ties in one direction inside of this auxiliary variable. Now the other one here, we would have the negation of P or Q, or our auxiliary variable x0. Now if we push that negation in using De Morgan's rules, we have not P and not Q, or x0, right? Now, what this again is saying is that, actually, let me push it one step further here using distribution. And so we would have not P, or our auxiliary variable x0, and not Q, or our auxiliary variable, right? Now these two parts in here should look fairly familiar, right? It's just the negation when we're trying to remove an implication. And so if we were to put this back in implication, just to get a sense of what's going on here in the logic, we would have the fact that P implies x0 and the fact that Q implies x0. Right? So if you have either P or Q, it's going to imply that x0 must hold as well. And this covers all of the 3 positive cases. And so you can see introducing auxiliary variables can be done by having this if and only if. It's an implication that goes both different ways. And the arbitrary pattern for this is your variable holds if and only if an entire formula holds. And then we can apply all of the common rules that you've already learned in the course. So I've shown here what happens when we have an auxiliary variable that's mapped to a simple disjunction. I want to show what happens in 2 other cases. And so the first is if we have an auxiliary variable mapped to a conjunction. It's very similar to what we have. So if we have x1 if and only if P and Q, right? The way we would break this down is to say x1 implies p and q. And to break that down further, not x1 or p and q. And if we were to use distribution, we would have not x1 or p and not x1 or q. Right? And so this is one form of the implication that goes. And the final case is going to be if we have an auxiliary variable x2 and we want this to equate with the negation of a particular proposition, right? So not p. Then we would have x2 implies not p, and we would have not p implies x2. I guess I missed one case up here in that, yeah, let me just finish this up. The one final case up here is going the other direction. We have not x1 implies p and q, but we have p and q implies x1, right? And putting that down using the rules that we know, not p and q or x1. And if you push the negation in using De Morgan's, you have not p or not q or x1. Right? And so here we have one sentence, and here we have another sentence, another formula. And up here it's even simpler, right? x2 implies p, that means we're going to have not x2 or not p, sorry, not x2 implies not p. And the other one we have p or x2. And really this is just the not p, and those two nots cancel out, right? And so the reason why I go through these different examples is it shows what we can do if we want an auxiliary variable tied to a disjunction. It shows what we do if we want an auxiliary variable tied to a conjunction. And it shows what we do when we have an auxiliary variable tied to a negation. Now with those three simple cases, what we'll see in the next lesson is how we could put all of this together to have a new way to compile conjunctive normal form from an arbitrary formula that we start with.